Hello, I am Juhee from Seoul National University. I am grateful for this opportunity to present this talk, ARM MTE, the end of memory corruption, not yet. I am a PhD student at Seoul National University in South Korea. My research interests include general software system security. This research was conducted in collaboration with people from Samsung Research, Jimbom Park, and Tae Kim, and also people from Seoul National University, my advisor Byung-Young Lee, and my colleagues Xiyeon Ro, Jae-Young Chung, and Young-Ju Lee. In this talk, I'll first introduce new ARM memory tagging extension and how it works. Then I'll explain the Tic Tac MTE tag side channel attack we discovered from Google Pixel devices. Finally, the real-world MTE bypass attack in Google Chrome, and I'll also talk about vendor responses and mitigations. Memory corruption attacks have been the most common and severe threats in software systems. In 2014, Heartbleed affected millions of servers by exploiting a buffer overread. After 10 years, regression bug was discovered, which can compromise any SSH server. Bad Binder and BlastPass also enabled zero-click attacks on Android and iOS mobile devices. So what is memory corruption? Normally, a program accesses memory objects through pointers, and if the pointer points to an object that is intended to point to, the access is valid. However, if the pointer points to an out-of-bounds region, the access is invalid, or the object is freed and the pointer is accessed after that, the access is also invalid. So from the early days of buffer overflows to the recent ROP and data-only attacks, attack techniques have evolved, and in response, defense mechanisms like stack protections, ASLR, and CFI have been developed. And in recent years, hardware-based defenses like Intel MPK and ARM PAC have been introduced. Last year, ARM memory tagging extension, MTE, became publicly available. Google Pixel 8 and 8 Pro are the first MTE-enabled devices. And MTE has been a hot topic in the security community. Companies like ARM, Google, Microsoft, and not to mention the academic security researchers have been anticipating MTE to be a game changer. So why is MTE special? It's because MTE is a hardware-based memory corruption detection, so it is fast and compatible, requiring minimum effort to adopt. MTE basically operates using a lock and key mechanism. Each pointer contains a key and each memory object contains a lock. And MTE ensures that only the valid pointer can access the memory object with the matching key and lock, preventing other invalid access. To achieve this, MTE introduces memory tagging. For memory tags, a dedicated memory region stores a 4-bit tag for each 16-byte data. And a pointer stores the corresponding tag, in its upper unused bit. This is possible because the address space are usually around 48 bits, so the top bits in the 64-bit pointer are unused. So ARM uses that space to store the MTE tag. And there's a new instructions to create random tags and low store memory tags. Using them, a program can assign a random tag to each object and the pointer. Then when the program accesses the object through a pointer, the MTE hardware checks whether the pointer tag matches the memory tag. On a valid access, the tags match, no fault is raised. On an invalid access, the tags mismatch, and the CPU raises a tag check fault, which crashes the program. So with MTE, to exploit a memory corruption vulnerability, the attacker would now need to bypass the MTE. How to bypass MTE? One way is to exploit tag collision. Since the tag is only 4-bit, there are 16 possible tags. So if the objects are randomly tagged, there is a 1/16 chance that two different objects have the same tag. So the attacker can wait until the tags collide and trigger memory corruption. Another way is to corrupt the pointer tag. So if the pointer can corrupt the entire pointer, the tag can be set to match the target object's tag, and it will bypass MTE. Here, the biggest challenge is that the memory tag is randomly created at runtime, and the attacker does not have knowledge of it. On brute force attempts, the program would crash 15 times out of 16, so the success rate would be around 6%, which can be too low for zero-day attacks where the attackers does not want to reveal their crashes. Therefore, a successful MTE bypass requires a reliable way to leak the tag of any address. To solve this, our approach mainly leverages two common CPU features. First, we exploit cache to leak tag track results with a cache side channel. Second, we exploit speculative exclusion to avoid crashes. Let's first take a look at the cache side channel. Cache is a small and fast memory that stores recently accessed data. It is located between the CPU and the main memory. When the CPU accesses a memory object for the first time, it fetches the object from the slow main memory, then caches the object in the cache. So the memory access would be slow, but when the CPU accesses the same object again, it directly fetches the object from the cache, so the access is fast. So with this timing difference, we can construct a cache side channel, which simply measures the time to access a pointer. If the measured time is fast, it means that the object is cached and has been accessed before. And if the measured time is slow, it means that the object is not cached and has not been accessed before. So we can exploit cache side channel to leak whether an address is accessed. Next is the speculative exclusion. Assume the CPU executes a code in the left side and is currently executing the line pointed by the arrow. Since the CPU has encountered an if statement, it needs to decide whether to take the true or false branch. Here, the condition value is unknown for a long time. Waiting until it is ready would be a huge waste of time and CPU resource. So the CPU speculates on what will happen next instead of waiting for this condition value. If the CPU speculates that this condition is true, it executes the true branch. And on a load instruction, the CPU would dereference the pointer and track the pointer's tag with the memory tag. And here we assume a tag match. And then the object is loaded to the CPU. But since it's loaded by a speculative exclusion, the CPU holds this object in a speculative state. And when the condition value arrives and it is true, the speculation is correct, then the CPU confirms the state to the actual evaluated state. Here, when the condition value was false, the code shouldn't have been executed. So the CPU discards the speculated state and reverses the execution to the correct path. However, the CPU does not revert the cache state, so the memory object is still cached. Here, what if a tag track fault occurs in the speculative exclusion? Assume the CPU speculatively loads an invalid pointer with an invalid tag. The pointer tag does not match the memory's tag, so the CPU raises a tag track fault. But here, the fault does not crash the process immediately because it is raised during speculative exclusion. There's a possibility that this code shouldn't have been executed. So when the condition value was false, the CPU reversed the execution and discard the tag track fault. This means that the tag track fault does not crash the program in the speculative exclusion. Now, leveraging speculative exclusion, we can trigger tag tracks either for tag match or mismatch, but never crash the program. Now, combining cache side channel and speculative exclusion, we can construct an MTE side channel attack. In this attack, the goal is to leak the memory tag. Assume we have a track pointer that points to a track object, and we want to leak this memory tag of the track object. To leak its tag, we're going to access this pointer in two cases. Case A with a valid tag, case B with an invalid tag. And then we're going to see if there's any cache difference between the valid and invalid tags, so that we can determine whether the pointer contains a valid or invalid tag with the cache side channel. However, if we simply access this track pointer, both cases would cache the object regardless of the tag's validity. So there is no cache difference, so we can learn nothing. But if we add additional memory access after that, say a test pointer, will there be any cache difference? To verify this, we're going to run this code shown on the left, which triggers speculative exclusion in the true branch. In case A, the track pointer's tag is valid, so the CPU speculatively accesses the track pointer, and the object is loaded into the cache, and the CPU tracks the tag. Here, the tag is matched. Then the CPU resumes the execution, so it accesses the test pointer at the test block. Here we also assume the tag track result is matched. So in the end, when the CPU reverses the execution, the cache would contain both track and test. In case B, where the track pointer tag is invalid, when the CPU speculatively accesses this track pointer, it would experience a tag track fault. Here, the CPU does not have any reason to execute the next instructions, because if it was a correct speculation, the fault would be synchronously caught by the CPU and the test block will not be executed. If it was a wrong speculation, the CPU would anyway revert the execution. So it is possible that the CPU stops the speculative execution here. If so, when the condition value is evaluated as false, the cache would contain only track object, not test object. Now we can use cache side channel. If you measure the access latency of test pointer, it would be fast on the valid tag, but slow on the invalid tag. From this difference, we can leak whether the tag in the track pointer is valid or invalid. The key question is whether the new MTE chips contain the tag leakage side channels. Previously, an attack called Pac-Man leaked ARM pointer authentication code with a similar side channel attack, so it is possible that ARM chips have the similar side channel issue again with MTE. So Google Project Zero conducted an analysis of the MTE hardware, including the search for the tag side channel, but they have failed to find the hardware tag side channels. They have tested a code consisting of the track pointer access and then a dependent test pointer access, and they varied the distance between them, but this did not generate any cache difference. So what we did was finding out what should be in the green part to induce the cache difference between the valid and invalid tags. As a result, we identified two memory access patterns that create such differences, which we call as Tic Tac Gadgets. And also, research group VSEC also orthogonally discovered one of our gadgets, and ARM equally acknowledged the discovery from our group and VSEC. So this is our first gadget, Tic Tac V1, which contains multiple loads and an instruction gap. First, the track block contains two or more instructions, load instructions, and the following gap block creates 10 or more cycle gap by repeating the OR instructions. Or it can be any other instructions that creates this 10 cycle gap. After that, the test block accesses test pointer, either dependent or independent to the track block, or either by a load or store access. And the graph in the right shows the test pointer cache hit rate after this gadget based on the number of track loads and the type of test instructions and the length of gap. Here we observe that the cache hit rate drops on every tag mismatch cases when the track block had multiple loads. And as pointed by the arrows, this drop occurred after about 10 instructions in the gap, which means it needs 10 cycles to see the cache differences. And the larger the number of tag track faults, the larger was the cache hit rate drop. So this result shows that when the CPU experiences 2 or more Ttrack faults, after about 10 cycles, test pointer is not accessed. And what's more interesting here is that when we examined the measured access latencies of the test pointer, we observed that the cache misses occurred periodically with the invalid tag, and this period was shorter with more Ttrack faults in the track block. So therefore the cache hit rate dropped more significantly with a higher number of Ttrack faults. And this result had multiple odd characteristics that cannot be explained with our previous knowledge. One, why do we need multiple loads? 2, why there is a 10 cycle CPU cycles gap? 3, why are the results periodic? So to analyze this root cause, we first listed the CPU features triggering speculative memory access. First, speculative exclusion. The CPU predicts the branch outcomes and speculatively excludes memory accesses. So one hypothesis is that the CPU stops speculative exclusion on Ttrack faults. Another factor is hardware data prefetching. Modern CPUs learn the memory access patterns from previous access history and prefetch data to reduce the memory latency. So the second hypothesis is that data prefetching stops by Ttrack faults. The challenge here is that the ARM CPU is black box, so its internal logic is not publicly known. So it's difficult to pinpoint the root cause of this unusual behavior. In the end, I ended up using 2 methodologies, 1 Appalation Study and 2 patent review. First, an Appalation Study is a methodology used to evaluate the contribution of individual components of overall performance of a system, and it's commonly used in AI research. But in our case, since the baseline CPU has both speculative exclusion and data prefetching enabled, it would be helpful if we disable one or both features to test the behavior persists. Speculative exclusion can be disabled by inserting a speculation barrier instruction, which is an instruction that that blocks the speculative exclusion after the instructions following the barrier. And the data prefetching can be disabled by changing the access pattern. This table shows the result of our Appalation study. There's 2 phases when we trigger speculative exclusion. First, branch training phase. We repeatedly execute the gadget with M1, the condition pointer, as true, and to train the if branch to the true path. And then in the speculative exclusion phase, M1 is set to false, and the CPU speculatively executes the gadget. So in the baseline, where both speculative exclusion and data prefetching are enabled, when M2 had a valid tag, M3 was cache hit, while with an invalid tag in M2, the M3 was periodically cache miss. Next, we disable speculative exclusion for the test block by inserting a speculation barrier before the test. And so this prevents the CPU from speculatively executing test access by inserting the barrier, but the CPU can still prefetch data using data prefetcher. And here the result was the same. So this tells that the root cause may not be the speculative exclusion. Then we disabled both speculative exclusion and data prefetching by changing the memory access pattern in the speculative exclusion phase from M3 to M4. Surprisingly, M4 always resulted in a cache miss, which is kind of obvious because we disabled all the speculative accessing mechanisms. But if we compare this result with the previous one, we can see that the data prefetching is the root cause of this behavior. Great, I could have ended this experiment here, but just to be thorough, we re-enabled this speculative exclusion by removing the barrier. So now we only have data prefetching enabled. So, but the result was the Tic Tac we want behavior reappeared. This shows that speculative exclusion is also a root cause. So we concluded that both speculative exclusion and data prefetching are causing this behavior. So to get deeper insights into why the CPU reduces speculative exclusion and data prefetching on Ttrack faults, we reviewed relevant patents filed by ARM and found one that describes a similar behavior. This patent is titled Prefetch Mechanism for a Cache Structure. It introduces a concept called a wrong path event, which provides a hint that the processor pipeline may have fetched one or more instructions that do not require exclusion. When we think about it, detecting Ttrack faults as a wrong path event and reducing CPU speculation can enhance performance in some cases, for example, in loop end detection. This also answers our earlier questions. Why do we need more than 2 laws? I guess multiple Ttrack faults, not only a single Ttrack fault, are treated as a wrong path event. Why do we need 10 cycle gap? Maybe there are instructions already fetched in the CPU pipeline, so the CPU is executing them, or there must be some latency of the wrong path event detection. And what about the periodicity? This patent further explains that there is a confidence value for each prefetch pattern, and which increases if the data access pattern is repeated. And although not explicitly stated in this patent, it is possible that the CPU reduces the confidence level of an access pattern when it detects such a wrong path event. And when the confidence is under a certain threshold, the CPU may remove the pattern, but this pattern and the confidence is reinitialized when it is observed again, so this can generate a periodic behavior. The second gadget we found, Tic Tac V2, triggers the store to load forwarding behavior in the CPU. So in the check block, it stores a value to a check pointer, and then it immediately loads the value from the check pointer. And after this store to load behavior, the test block accesses memory access dependent to the value forwarded by the check block. Here, the CPU often optimizes the performance using internal store and load buffers, which log recent store and load instructions. So if a store and the following load instructions are for the same address, the CPU directly forwards the data from the store to load instead of accessing the cache. And we've observed that when Ttrack fault occurs during store to load forwarding, either in store, load, or both, the dependent access in the test block is not executed, which means the value is not forwarded. And we suspect that there is a logic in the CPU that blocks this store to load forwarding behavior on Ttrack faults to mitigate some meltdown issues. Additionally, there was a condition that the store and load instructions should be close within 5 assembly instructions, and we also found a patent that is relevant to this behavior, but due to time constraints, please check our paper for that. Now, based on these MTE side channel gadgets we found, we can construct real-world MTE bypass attacks. We developed real-world gadgets and MTE bypass attacks on 2 major systems, Google Chrome and the Linux kernel, which support MTE random tagging. In this talk, I'll present the attack on the Google Chrome V8 engine that constructs a tag leakage gadget from JavaScript code and leaks MTE tag of the render process memory. We also found a gadget from the Linux kernel and developed an attack, so it's explained in our paper. So in Google Chrome, the render process consists of the V8 JavaScript engine, the Blink rendering engine, and other third-party libraries. Attackers can provide malicious JavaScript, HTML, and CSS data, which can trigger memory crunching vulnerabilities in each code base. Since this JavaScript code is compiled and run by the V8 engine, it has been the most accessible target. So the V8 Sandbox is developed and applied by default to Sandbox the untrusted exclusion. It ensures that no JavaScript can access the rest of the render memory. But the Blink renderer and third-party libraries also contain a vast amount of code, potentially containing memory corruption vulnerabilities, so we can still exploit them even if the V8 Sandbox is enabled. Currently, Chrome optionally supports MTE random tagging in the renderer memory. So enabling this feature will tag the objects in Blink and third-party libraries. Here, our idea is that although the V8 Sandbox prohibits JavaScript from directly corrupting these objects, if the JavaScript can speculatively access out of the V8 Sandbox, we can construct a Tic Tac Gadget to leak the MTE tags and exploit memory corruption vulnerabilities. The challenge here is to speculatively accessing beyond the V8 Sandbox, whether it would be possible. We found it possible because the V8 does not entirely enforce the sandbox to the speculative path. So when this JavaScript U8 array is accessed, the V8 sandbox V8 engine first obtains the array element address from a 37-bit compressed pointer, which resides in a 128 gigabyte sandbox, and it adds the pointer compression base. And then it performs a array range check. Here the array length is 35-bit integer, but the provided index can be 64-bit out-of-bounds index. And the range check can be speculatively bypassed because there is no index masking or speculation barrier, so we can speculatively access arbitrary 64-bit address. This allows the construction of Tic Tac V2, and it also enables Spectre V1 in the V8. This is our Tic Tac V2 created using JavaScript. First, the attacker prepares an 64-bit out-of-bounds index, and the check array is accessed with this index so that it can represent the attacker-controlled check pointer. And then we wrap this access in an if statement because the V8 would detect this out-of-bounds array index and raise an error if it was a normal exclusion. So to avoid this, we wrap this access with an if statement. Here the V8 does not raise an error, but the CPU does access speculatively this out-of-bounds address. And then the gadget triggers total forwarding, and the forwarded value is used as an index of the test array. In this way, the test array becomes the test pointer, and it constructs the tag leakage gadget. And to exploit this gadget, the attacker can construct a tag leak function like this that leaks the tag of an arbitrary address. It iterates over all possible tag values from 0 to 15, and it creates an out-of-bounds index, and then trigger the gadget. And depending on whether the tag is valid or invalid, the test array will be accessed or not. And if we measure the access latency, we can leak the correct tag of arbitrary address. And leveraging this tag leak function, we can exploit an existing out-of-bounds access vulnerability. First, the object leaks the vulnerable object's tag, and then it leaks the neighboring target object's tag. If they do not match, the attacker reallocates the target object until they are matched, and then it triggers the out-of-bounds access, which bypass MTE. So this demo is the heap overflow exploitation. This is an original memory corruption with MTE enabled without tag leakage. If we trigger the heap overflow, the process crashed because of the MTE tag mismatch. But with our MTE tag leakage gadget, we first leak the vulnerable objects tag and the target objects tag. Oops, sorry. We leak the tags of the vulnerable object and target object and reallocate until they match, and then trigger heap overflow. Here, we do not experience any crash, so we can exploit memory corruption as if there is no MTE enabled. So we reported this issue to relevant vendors. First, ARM acknowledged these MTE side channels in multiple cores, but they cannot leave comments on our root causes due to licensing issues. They also clarified that MTE tags are not considered as secrets, so leaking MTE tags is not a security vulnerability, but they expected the cost of the fix to be low and recommended the vendors to fix it. Google Android security team, however, acknowledged this as a hardware flaw of Pixel devices, but they still consider MTE as a strong mitigation against limited shot exploits where side channel attack is extremely challenging. Google Chrome V8 team concluded that MTE side channel attack and the Spectre does not violate the V8 security model because data confidentiality, including MTE tag, is out of scope for the V8 sandbox. So they only care about the data, corrupting data. And for the tag leakage issue, they mentioned that they currently do not have plans to adopt MTE on render due to several reasons, including the side channel issues like this. But I think for the side channel issue, we think the V8 can mitigate this with speculation-aware sandbox design. I'll explain later. So to fix this vulnerability, the MTE tag leakage vulnerability in hardware, there are two ways. First, always blocking the speculative memory access after a speculative tag check, which is bad because it's disabling all CPU optimizations after a memory access, so there will be a huge performance sacrifice. Another way, a better solution, is always allowing speculative access after a speculative tag check. This does not turn off speculative exclusion and data prefetching, so there will be no performance sacrifice, but this brings a meltdown-like issue because the data being loaded under tag check fault can be speculatively used and leaked through the cache. But I guess this is the way the current MTE operates on normal cases, which does not leak tag, so this is the intended design of MTE. And to prevent this MTE meltdown issue, I guess we should not rely on MTE for keeping data secrets for now and wait for another Spectre mitigation in the hardware. So to mitigate this issue in the software side, it is possible to scan the gadget from the target binary and insert a speculation barrier or dummy instructions to invalidate the gadget. Or if the target program can isolate an attacker input, like the V8 sandbox, it should completely mask all the pointers, indexes, and memory accesses to isolate untrusted data under speculative exclusion. So to wrap up, are we at the end of memory corruption? ARM MTE is indeed a promising security feature, because no previous techniques have been able to provide this level of security and efficiency. However, we have shown that current MTE hardware contains tag leakage side channels to allow the attackers to bypass MTE random tagging. So the answer is not yet, but I guess we're moving towards the end of memory corruption. There are next steps, like deterministic tagging that does not rely on random tags like sticky tags, which will be presented in the memory security section today. Or we can keep random tagging scheme after we fix Tic Tac Gadgets and prevent brute force attacks on random tags. So thank you for your attention. If you have any questions, please.
All right, now there's time for questions. I guess I have a question. Do you think that the introduction of MTE in general could make exploiting Spectre easier? Because now we have like this easy fold here gadget. Or do you think it's not really relevant?
Exploiting Spectre I think MTE does not make it easier to exploit Spectre. It would be similar. I actually didn't understand what you...
I think there was like some Intel SGX feature or something like that, where there was like an assembly instruction was like, okay, now start speculatively execution. While here we kind of have it the other way around, like, okay, stop speculatively execution here if I load invalid tag. Or do you think it's not really mattering for other general Spectre exploits?
So this is the side channel I presented here is only for the tags confidentiality. So I guess data confidentiality is another topic.
Okay, thank you. Any questions? All right, maybe I have a second question. How would you exploit the speculative side channel across exception level boundary? Like, how would you target the kernel to do the cache leakage and detect that whether something is in the cache or not? Because as far as I'm aware, PAN prevents loading user mode, fetching even speculatively user mode memory into the kernel.
Yes. So MTE tags, when we exploit kernel MTE tags, when we want to leak it, we have to get into the kernel process because it's in the kernel process memory. So to do that, we exploited the syscalls to enter the kernel space. And then to find the exploitable gadget, easy to exploit gadgets, we especially collected those using copy to user or copy to from functions.
All right, thank you. All right, I guess there's no more questions. Thanks again for your talk.